Hello, everyone. My name is Alexis Gallardo, and today, along with my team composed of Wesley, Deklich, Marc, Revilla, Alessandro, Avendano, and Amitesh, Bharati, we'll be presenting the limitations on the meteorite pairing process. So, meteorite pairing is a process of identifying the many fragmentations of a meteorite separated during atmospheric travel or upon collision with terrestrial land. The pairing process is accomplished through a thorough comparison of properties such as petrochemical composition, mineral composition, cosmic ray exposure, as well as thermoluminescence levels. The pairing of meteorites is important to us because it allows us to understand the journey of a meteorite from its origin to its final destination, the terrestrial age of the meteorite, as well as the early formation of the solar system. Scientists have developed new forms of tackling the challenges of pairing. These include the use of genetic nomenclature algorithms, as well as the Bayesian classification system, which both automate and ease the challenges in the pairing process. This research covers in depth the many challenges scientists face when it comes to pairing located samples and the solutions to the many complications involved. Thank you very much.
Meteorite classification groups similar meteorites together. It evolves as the knowledge and data of meteorites expands. A variety of methods are used to classify meteorites, but the groupings based on these datasets are not always consistent with each other. A successful meteorite pairing is denoted by finding absolute similarities between two or more meteorite fragments in the properties tested, but a negative piece of evidence can make these similarities redundant.
One of the main difficulties of meteorite pairing is the lack of a clear set of guidelines. Scientists use a variety of analytical techniques to determine pairs, and yet some scientists might be able to pair a meteorite while others cannot. For example, Benoit considered the primary characteristics as shock rate, phaolite, and ferrosilicate content, while Bogdanovsky used mineralogic composition and textures of Denvaux to compare it with other primitive chondrites. A proposal for a global meteorite pairing system falls under three categories: physical characteristics, geographic proximity, and recent space history. Human error and inappropriate equipment can lead to failures when classifying meteorites. New advancements in image processing, deep learning, and computational techniques allow for automating this process. Artificial intelligence can scan meteorites and reduce the work of scientists when given an appropriate, generous dataset. Furthermore, even if a meteorite is paired, there is still uncertainty due to the lack of data. Elephant moraine 85721 was originally classified as a brecciated eukaryote by Paul Warren from UCLA, but it was later recognized to be a brecciated lunar volcanic rock. Scientists have added a generic algorithm that assigns a score to pairings.
The implementation of a global meteorite database could greatly improve access to samples and their analyses. By using drones equipped with light detection and ranging, or LiDAR systems, searching open areas, such as Antarctica, could be made far faster. Finally, AI analysis can compare thousands of meteorites at once and set an equal standard of probability for each pair.
And as we find out more about the limitations of the meteorite pairing process, there's a few things we can try to implement in order to make this easier for scientists. Firstly, we have artificial intelligence, so by using photomicrographs as well as other computational techniques, we can try to make this process quicker and a lot more automated for these scientists. There's also genetic algorithms, which are often compared to natural selection in the sense that pairings are put up against each other for competition and the best pairings come out on top. There's Bayesian classification, which uses statistics and probability in order to find correlation between variables, and this also leads to newer classifications such as the Bayesian belief networks. We have the scoring system that was previously mentioned, in which pairings are assigned a letter depending on how strong they are, and there's also technology that can be used outside of the lab in the fields, such as in Antarctica or in deserts, in order to find these meteorites quicker, such as drones. And again, the purpose of this is to not make this process fully automated, but to try to make it a lot easier for
My
scientists.
team and I gained a lot of good experience from our time at SEAS. One of the best features of the program is how each intern is taught how to conduct research and find scientific papers which are suitable sources. On the other hand, a challenge the group ran into was the team dynamics and coordination. Learning to communicate effectively was key.
The STEM enhancements in our science program allowed us to explore topics not offered in traditional high schools. It was very exciting to collaborate with talented students and mentors from all around the United States. Not to mention, it sparked new interests in astronomy, earth science, and interdisciplinary research, and also solidified future career interests in science, math, and engineering.
Thank you to mentor Susan Foxworth, as well as everyone else who organized and ran the SEAS internship. So Selena Miller, Margaret Baggio, and the NASA Texas Space Grant. And thank you to all of the NASA ARIS speakers who gave presentations throughout the internship.